Hey, physics peeps, I'm back at you with electromagnetic induction. So if you remember way back when Ørsted discovered that electricity produces a magnetic field around the current, and then it also works the other way. So along came Henry and Faraday, who lived just shortly at the end of Ørsted, and they discovered that it worked the opposite way, that you could use a magnet to create a current from that. So Ørsted went from electricity to magnetism. Henry and Faraday went the opposite way, that you could take magnetism and produce electricity. And the way that works is that we would have this solenoid or all of these loops of wire that are here on the screen, and you would have a magnet, and that when you move the magnet based on those loops of wire, that changing magnetic field cutting across all of those loops of wire induce or push the electrons along. The faster the motion, the more the current. The more the loops, the more the current. So when you have that, if you just have the magnet sitting there, nothing happens. It has to be moving to begin with and for you to get anything out of it. So one of the simulations I want to show you here is a FET simulation. So we use this in class a lot, and this is the Faraday's law one. And if I pull this over to here, then you can see here's my light bulb, here's my magnet, and a lot of you would have experienced this whenever you built your wind turbines for the class project. So here you'll notice that as I move that magnetic field across the loop of the wire, you'll see that it is inducing a current there. And or if I make this even more visible, if I click on the field lines, so remember that it's strongest at the pole. That's why you see a lot of lines there. And then it gets weaker and weaker and weaker the further out and the further away you get. And it's that change in the field lines as those field lines cross over the wires that induces that current. So as I get it closer, you'll notice that I get a little bit brighter. And then if I move it in and out, notice that that changing is bright, bright. Now, for some of you, you had the vertical wind turbines where you had it this way with your fan blade up here and it was spinning this way and the magnets were down here and the loops of wire were down here. And so basically all you were doing is going this way across your wire. Notice how that's not giving you much of a light there. But for some of you, you put your magnets inside the loop of wire and you have the magnets rotating. And if you notice, when I start spinning this back and forth really quickly, I get a lot of induced current from that. And so that's really one of the ways you can get a strong one. And again, you want those loops tight. The more loops that you have, the more induced current that you're going to have, and so on. So this is a site that you can visit real easily if you just Google PHET, Physics, Engineering, and Technology, FET, simulation, Faraday's law, then you can go to that to see that. Okay, so Faraday's law, Maxwell comes along, he lives a little bit after that, and he puts all of these together into four pillars of what we would call electromagnetism. And he lumps together this Henry and Faraday's work into what we would call Faraday's law. And he says that the induced voltage in a coil is directly proportional to the product of the number of the loops. So we have the number of loops here, and the area of the loops, and the rate at which the magnetic field is changing. So what we would do is we would say, hey, this magnetic field is changing based on the A and the B, the field inside a certain area. And a lot of times we will lump that together and say that B and the A is what we would call flux. So it's the amount of magnetic field going perpendicularly through a certain area. And if you picture this as maybe like a river, if you're picturing the river bed and then the river is going this way towards you, so the flux will be like how much water is passing this this cross section at one moment. Well, the same thing in this case, we're looking at how much magnetic field is crossing a specific area at that one moment. So when we put that together, we have the B times the A, and we could have the number of loops in the front of this here. I can't get my pen to work, but that would be the number of loops in front. And then you'd have B times A over the change in time. And then, or it could be that flux divided by the time value that you have for that. And so that would be what we would say is Faraday's law. We would apply this then into motors and generators. So we would take, in this case, we have our magnets on the outside here, which are the blue and the red ones, and then we have these coils of wire on the inside, and as the wire is spinning on the inside, it has a current being induced in it because of the magnetic field that is there. So I have one of these here. I don't know how well you can see it, if I can get it up there. So there you can see, and this was just the end that I pulled off of. So I pulled that off of the end there, and you can see that. And then if I pull this whole, I can't even get the shaft out. So I'll grab another one here. If I grab another one, so you can pop the whole end out, and notice that we have all these coils, those 3 coils of wire, and then these parts here that are magnetic, and then there are the 2 magnets in here, and it's that spinning of the magnetic field that the 2 magnets on the inside create. The wire changing its motion on the inside of that causes it to spin. So in a generator's case, a generator is where we would put mechanical energy in and get electricity out. So on the end of, like maybe on this end, we would put fan blades, and as that's spinning, we would get electricity out of the end of this. Now that's the basis of all of our modern technology, is what is going to cause that shaft or that axis to rotate. So maybe it's wind coming in and spinning it. Maybe it's coal down here burning, and that heat rising causes it to spin. Maybe we put this at the bottom of a dam and we have the water coming over it causing it to spin. But all of those sources of electricity are all based on the fact that we have this coil of wire and the magnet, and that as that coil is spinning in the magnet, then that gives us the electricity out the other end. Now, interestingly enough, a motor is the exact opposite. It's where you would put electricity into this end, and you would get the spinning on the other end that would be like a fan. So if you went home and you actually hand cranked your fan, you would be recreating electricity on the other end and sending it back into the power grid from there. Now, theoretically, could you hook these together then and have them run forever? Hook a motor, which creates electricity, into a generator, which creates mechanical energy to put back into the motor? And the answer to that is nice thought, but it's not going to happen. Because of the conservation of energy, you're going to lose energy in that process. And by losing, meaning like not like a poof, it's gone, more like a losing, like we can't do anything with that energy anymore because it heats up the parts, it heats up different aspects, or the motion of the air. We can't get the energy of that motion back again. And so that is that. So key ideas, we have Faraday's law, that is a current can be induced in a wire when there's a changing magnetic field, and that the faster the motion, the more current, and the more loops, the more current. That is described by this relationship here, and this E is really nothing more than the voltage. And then lastly, a motor has electricity that comes in and mechanical energy out, and a generator has mechanical energy in and electricity that comes out. And that, in a nutshell, is Faraday's law.